I'll do this. I'm going to share, see how that works. Okay. So can we all see my terminal now?
Yes.
Hopefully. And is the font big enough?
Can you make it one size bigger?
Okay.
That's a little better.
Better? Yep. So we're going to go into 2D greens functions. So we have here, there's a Readme at the top level directory, which pretty much describes everything in here. This is also described in the manual, but this is, I believe, a fairly comprehensive Readme, and it does talk about the mesh generation, which is the first thing we're going to do. And then, yeah, then we'll continue on with those steps. So we'll look first. We're going to do the reverse slit example this morning. So you'll see for this one, we have a number of different journal files, never mind the qubit ones. But I believe this morning in the 3D hex 8 example, you would have had, I believe, a geometry.journal file and probably a mesh file. In this one, we have a little bit more. We have a geometry file. We have a gradient file because we're producing a graded mesh that increases the mesh size as we move away from the part of the fault that we're interested in. We have another part, this create BC, that creates the boundary conditions that we want. And then finally, the one that calls all of these is this mesh_try3.journal file. So I'm going to open up Trellis. So hopefully we can see Trellis. The first thing which you might not see on this screen, I'm setting my directory. I've already got it set for this directory where we are. Examples 2D greens functions reverse. Choose that directory. We're going to open up, we'll open up our top level journal file, try3.journal. And what you'll see in here, the first thing that journal file does is play back our geometry. So let's open up the geometry file and see what's in there. Okay. We're using a feature of qubit and Trellis called ID-less geometry, and I don't really want to get into that too much, but it's a way of avoiding having to know all the like curve and surface numbers and things like that. So what we do a reset to make sure we have cleared anything we might have done before. We'll turn undo off. We're going to turn on the ID-less journaling. And then the first thing we're going to do is create a block that's 150 kilometers wide. Oh, sorry. Up here we said units SI, which allows us to specify things in terms of kilometers. So we have 150 kilometer wide block. It's 80 kilometers high. And the length is the distance into and out of the plane, actually. So that's 10 kilometers. Then we're giving it fault parameters, a width of 30 kilometers, a dip angle of 45. So let's first, we'll do everything starting from here. We'll go ahead and make our block. And then we'll move it let's see, did we use Apropos this morning? I don't.
No, we did not.
Okay. So that's something that might require a little bit of explaining. It's just a simple calculator language that Qubit and Trellis include, and it allows you to do things like define variables. Like here we've defined the width of our block. By using this units SI, it also means that we can do it in units, in whatever units we want, and it'll translate it to SI units. So we define our block width, height, and length, width, dip angle, and it also allows us to compute things. Like here's our fault width times the degree cosine of our fault dip angle. That gives us our X offset. And then we create the brick using the dimensions we defined. We can get the ID of this volume. So if you look over here, you'll see there's all these variables. Let's see, where is ID? There it is. So that volume ID is just 1, which you could also see by going up here. Volume 1, that's just that. So there are a lot of useful functions in there, and it makes it, it's just handy to use. So now we've made our box, we've moved it to where we want it to be. Now we're going to create a mid-surface volume, which is just a surface that'll be halfway in between. It'll be between this surface and this back surface right here. So we'll do that. And then we're going to just delete the volume. So now we just have a surface, which is called a sheet body over here. Body 2, which is composed of surface 7. Now we're going to make a fault surface, which in 2D is just a curve. So we're telling it to split this surface that we just created and give it 2 points. So we'll do that. So we gave it 2 points in which to split this surface. So now we've got a curve in there. We are going to name this one fault extended, and then we're going to split the fault also at a position along the fault. So if I want to select curves, now we'll see we've split that curve, so we have it there and there. So this is going to be our main fault, this part up here, and this is just going to be an extension of the fault. We'll name it. So first we name this one. So if we look at so that's fault surface. We're going to name the other ones too. It's just handy to have your curves named so you don't get mixed up with the numbers that refer to them. So we'll name all of these. So now you'll see that we have all these named curves now. Edge, the positive X edge, positive or the negative Y edge along the footwall, and etc. like that. we're going to name a few of our vertices as well. So that's what we're doing right here. So now we can look at some of these. There's a vertex that we've named vertex fault top, vertex fault bot. And so this will help us in our meshing and in defining node sets, which we'll do later on. So that's our geometry. Now we've created that geometry. So that's what we would have done in our mesh try3 journal file. We have done everything in geometry.journal. Now we're going to set the discretization size. Our default is going to be 1 kilometer. We're going to use triangles to mesh this. And then this gradient.journal is going to give us gradients in the size of the mesh. So first we'll play this part here. This won't do anything that you can see, but it sets some of the schemes. Okay. Then we can open this gradient.journal file and see what's inside there. There we go. So there's our gradient journal. There, we can have in Qubit and Trellis, you can have these bias sizing functions. And so when you do that, you define like an initial size. You can do it several ways. You can define an initial size and the amount by which it increases, or you can define initial size and a final size. There are a number of ways, but this bias factor is how much the size increases as you're moving away. Also, here's another, so there's a variable that we defined in EPRAPRO. Here's a function that we're defining, which I'm not going to go through the details of it, but this helps us define a bias sizing function. So we'll just do these. And all those do is define some apropos variables. Then we're going to compute sizes at the endpoints of these various curves. Here's a vertex that we've named, vertex xpos. Then we're going to define sizing function values at the beginnings and ends of these curves. So here we'll just play these. These warnings are okay. They just don't like it when you redefine variables. Okay, curveball scheme default, that just means that it has no prior information. And then we're going to start setting sizes. So first we set this default size, which is, if you remember, dx was just 1 kilometer. That's our default size. Do that. You can, anytime you don't remember, you can look over here. There's dx, which is 1,000 meters. And then we'll set the bias on the curves that are extended from the faults. Okay, we've done that. And then we'll finally set the remainder of our. Sorry, I'm not going through this in more detail, but I think if I do, I'll run out of time. Now you want to see what you've actually ended up doing. So you can do so what this shows you is on all the curves, it shows you what your spacing is. And we've set this. You can see that we have fine spacing close to the end of the fault. We have coarser spacing around the far edges of the mesh, furthest away from the fault. And then also on the ground surface close to the fault, we have finer spacing. So that's what we've been doing with this gradient file. Now we can go back to our main file. So we've done the gradient, and now we're just going to mesh using those sizing functions. So there's the mesh that we end up with. The question is it a good quality mesh? And we can do this by looking at the mesh quality over here. Condition number is usually a good one to use. And you can see that it ranges from 1, which is ideal, to 2.15, which is not bad. But we're going to improve that by doing 1 round of smoothing. So this is, you first set the smoothing scheme, which we're here using the condition number scheme. Beta is your mesh quality criterion, and we're setting it pretty low, 1.3. And CPU time is the maximum number of minutes it'll try to improve the quality. So we're going to do that, and then we're actually going to impose that smoothing scheme. So we do that. And now if we look at our smoothing again, we'll see that we have a much better quality mesh. They're all much closer to 1 now, which is what we want. Then the create BC, that's the final part, and I know you've done something similar to this, so we're not going to spend a lot of time on that. It's the same as you did before. You define your blocks, and in this case, since we're 2D, we include all of the surfaces. We'll give it the name elastic, and then we're going to create all these different node sets. And since we've named our curves, we can just use, rather than curve numbers, we can use curve names like fault surface and things like that. So I'll go ahead and just do play that whole thing back. So now we have that. You can look quickly at your node sets. We have the fault right there. Fault edge. We need that for a fault that does not cut the entire mesh. And so in 2D, that's just a single node right there. That's the edge of the fault. And then we have our external boundaries. There's the X positive edge, X negative, and etc. like that. And then finally, we're going to export our mesh. I'm not going to do that because I've already got the mesh that we need. So before I move on to actually doing the simulations, do we have any questions? I'm trying, how do I see questions? Or Brad can just tell me.
No evidence of typing.
Good. Okay, so I'm going to quit out of Trellis right now, and we'll go ahead and start doing the simulations. Okay, so that was the mesh generation. If you look at the Readme up above one level, you'll see that what we're doing, we have the, first we generate our mesh, then we're going to do a forward simulation. And this is essentially creating synthetic data. So we're telling it, we have a spatial database that defines how the fault is slipping. And then we have parameters in eqsim.config that gives some other parameters for this particular problem. So we'll first look at our PyLith app.config. So these are just your regular journal things that you turn on. We're using a qubit mesh. It's going to be the mesh that we just created, mesh try3.exo. Just for fun, we're going to reorder the mesh to which can speed calculations up in some cases. This is a two-dimensional problem, so we've set our spatial dimension to 2. We continue down. The problem also has a dimension of 2. We're just setting some normalizer length scales. As you recall, PyLith uses non-dimensionalization to help scale the problem properly. We're giving it a length scale of 1 kilometer, which I believe might be the default anyway. Relaxation time does not matter much in this problem since it's a static elastic problem. And then we're giving it a total time of 0 seconds. Again, it's just a static problem, and a DT of 1 year. Okay, our materials. We just have one material where we have called it elastic, and it's an elastic plane strain material since this is a 2D plane strain problem. We give our elastic material a label, just call it elastic material. The ID is the ID that we just set in our createbc.journal file. We have a spatial database that defines the properties for this material, and it's going to be just a single property for the entire thing. And we're going to call that the properties, we'll label it as elastic properties. We also have to give it quadrature information. This is linear triangles, and so that's a fiat simplex element type, and the dimension of the cell type is 2. Then we have an array of 3 boundary conditions, and the boundary conditions we're imposing are just going to be roller boundary conditions. So we have our x positive boundary condition. We're just constraining the x direction, and we're using the 0 displacement boundary condition in PyLith, and then we give it a label. We do the same thing for the negative displacement on the x negative boundary. We constrain the x direction. Again, it's just 0 displacement in the x direction, and then give it a label. And then finally, for the y, that's our bottom boundary condition. In this case, we're just constraining the y component, which is direction number 1. Again, 0 displacement and a label. So that's just roller boundary conditions all the way around. Finally, we have our fault. So we have, we're calling our interfaces just an array with 1 component, which is fault. And then for this fault, we're giving it an ID number of 100. That's arbitrary, but we tend to use higher numbers for the fault. Give it a label. Now, also, you have to give it a node set of the buried edge, which we did in our createbc.journal file. So that's a single vertex, which we've given the label fault edge. And PyLith needs this information to generate the cohesive elements or cohesive cells. And so our fault, again, this is fiat simplex, which is just lines in this case. So the fault itself is just a curve. So that's a cell dimension of 1. Okay. Then finally, some information about the output. We're going to output the solution for the entire domain for the ground surface, which is just the positive y node set, and then also at a set of points that we're going to define. And so for each of these, you have to tell it The default is output for the entire domain, so we don't have to do anything for that. But if we're outputting for a set of points, we have to tell PyLith that that's what that means. And that says output solution points right here. Similarly, for the ground surface, we're outputting for a subset of the solution. And so that's what this is right here. We're going to output at a node set defined by the y positive nodes. Also, we need to specify what type of output we want. We want HDF5 output. So for the domain, we're telling it that our writer is data writer HDF5. We're going to do the same thing for the ground surface. We're going to have a data writer HDF5. Also, since this is a solution subset, we have to tell it which node set to use. So that's the node set called face ypos, which we find in our createbc.journal file. Finally, for the solution output at the points, we have to give it coordinate system information. It's a spatial dimension of 2. The units that we're using in our coordinate system are kilometers. We have to tell it that we want HDF5 output. And then finally, we're giving it a file name to get the point coordinates from. And we might look first at that point coordinates file after we're done looking at this file. Then finally, we give it information for the fault. The fault output, we also want HDF5 output. And then for the elastic output, that's the stresses and strains from the simulation. We're actually not going to output anything for that because it's not really pertinent for this problem. So we put in empty arrays for the cell info fields and the cell data fields. The info fields would be things like density, shear modulus, things like that. The data fields would be the stress and the total strain. And again, we're telling it to use HDF5 output, even though we're not going to output any fields. Then the final thing on here are our PET-C settings. And these are just the linear solution parameters that we're giving PET-C to use. So if you recall, I talked about the output points file. So that's this file here. So that tells us for both the earthquake simulation and generating our Green's functions, we need to tell it the coordinates of the points where we want the solution. And if you recall, within this file here, we said that we're going to give these coordinates in units of kilometers. So these units here are kilometers. So the first column is your station name. So we've just given them names A through L. And then your X coordinate and your Y coordinate. So in this case, this is just your vertical coordinate. And we're giving it a position that is just very, very slightly below the ground surface, because in some cases, due to round off, if you give it exactly 0, it may think that it's lying outside of the domain of your mesh. So for all of the Y coordinates we've just put it just barely below the ground surface. The other external file that we're using is this earthquake slip file. So this is just telling it how to slip the fault. So for 2D, all we have is left lateral slip and fault opening. So we're not going to have any fault opening for this problem, but we are going to have some left lateral slip. So we have 2 values, left lateral slip, fault opening. The units are meters. We're going to specify it at 4 locations. Our data dimension is 1, so that we're providing the information along the line. Our space dimension is 2. We're going to specify our coordinates in kilometers just for convenience. And again, our coordinate system spatial dimension is 2. So here is a point up in the air. So what we're saying is all the way down to 2.5 kilometers depth, or no, sorry, all the way up and down to 12 kilometers depth, we want a slip of 2.5 meters. And this is going to be a reverse slip. And then below that depth, and then that's going to taper from 2.5 to 0 between 12 kilometers and 15 kilometers depth. And then it's going to continue at 0 all the way down through the bottom of the mesh. Now, if we look back up in our, let's see, do we do it here? No, that's going to be in our eqsim.config file. Sorry, I might have jumped ahead. This is where we tell it, where we use the earthquake slip. So we're using fault cohesive kinetic fault interface condition. Our rupture slip function, that's the file we just looked at where we specify the earthquake slip. We're going to use linear interpolation. So in the file you just saw, it's going to linearly interpolate over this depth range from 12 to 15 kilometers depth. It's going to interpolate from 2.5 meters of slip to 0 meters of slip. We label it as final slip. The slip time is uniform, so that's very easy to do. We just tell it slip at 0 years time. And just rather than using a spatial database, we use a uniform database. And then finally, we just have our output file names. So we've already in PyLith app.config said that we're using HDF5 output. We've told it which node set corresponds to the ground surface output, where to get the point information for the output its solution points, and then the type of file to use for the fault output. So then that's all of, I believe, all of the files we need to run our first simulation. So you just do that by running PyLith eqsim.config. Now, I don't know if we went over this. Usually it's handy to also save a log file when you run a simulation, just in case you run into problems. So that's what I'm doing right here. Oh. Let's see. Oops, let me start a new one. There we go. Is that the same size? Or maybe one more? There we go. Okay. Okay, there we go. That, I'm guessing that part of that is probably off the screen. Is that correct? Anyway, we ran correctly. You can see there weren't any errors. We have our PET-C information from when we ran. And you can also look at your linear solution stuff. So what we just did is run our forward problem. Oops, not that one. Okay. There's our fault. And we'll open up the domain as well. Oops. So first we'll look at the fault. You can see that the slip we applied make that bigger. So let's so you can see that the fault slip is ranging from 2.5 meters along this part here, negative 2.5, and then we do have a variation over this depth range here from 12 to 15 kilometers depth, and then it goes to 0. And then the resulting displacement is shown here. So there's our x displacement. Let's look at the y displacement. So you have, you can see that you, if we zero that displacement, you have your up thrown block and your down thrown block. Then the other thing that we've done is generated the solution at these points here. So let's turn off the domain, and we'll make the points bigger. So these are the points where we've also computed the displacement. And if you want to see more what you've done, we can make a quick vector. We'll just go down here. The calculator in ParaView is pretty handy. So we'll do that, and then we can plot vectors that show what you've what we've done. Okay, scaling is probably going to be off. Let's try. Oops, that's too big. This just shows you what your surface displacements look like at your observation point. So this, essentially, these are fake GPS vectors that we've created, except that we've done it in 2D. So there's that part. Then the next part is generating our greens functions. Are there any questions about this part before we continue on?
No evidence of typing.
Okay. All right. So looking again at our Readme up above, now we're going to generate greens functions. So the files involved in that, we just have we have our PyLith app that we already had. Now we have a greens functions config file, which adds some additional information. Now, the first thing you'll notice in this, when we generate greens functions, we change the problem type. So you'll see here, rather than saying PyLith app, this now says greens functions. So because now the problem is a greens functions problem, this is how we're going to run it. So when generating greens functions, you do need the fault ID, which you've already provided in PyLith PyLith app.config. Now we're also going to change our fault interface condition. Rather than fault cohesive Connecticut, this is, did I say Connecticut? Kinetic. We have fault cohesive impulses. So that's where we apply units slip impulses at a specified set of nodes.
Charles, we do have a question.
Yes.
So we covered this a little bit this morning, and the question is related to the components given in the slip output versus the components in the displacement output.
Okay. So looking back at our para view, okay. For 2D output, we have displacement X, displacement Y. For 3D output, we do it as a complete vector, I believe. And so what I had to do to make displacement X and displacement Y into a vector, I had to use this calculator. For the slip, we have, if we go to the fault, the components are slip X, slip Y, traction change X, and traction change Y. So in 2D, we don't have reverse slip. We just call it left lateral slip, even though it's actually is reverse slip in this case. And then so that's the component we're looking at now. If we look at the Y component, it's 0. And that's because in 2D, that's the fault opening component. Same for the traction changes associated with those components. We have a traction change, which you'll notice occurs where you have the change in slip. And or you will have a little bit of traction change in Y, but it is associated with the fault opening component of slip. I don't know if that answered the question or not. Okay. Okay. So we have our cohesive impulses that we're going to apply. We're only going to apply left lateral slip. So our impulse degree of freedom is 0. And the amplitude is going to be provided in this impulse amplitude spatial database. So we'll look at that in a minute. But this is just specifying you might want values other than 1, or you might want a negative value, which is frequently the case if you want to represent reverse slip rather than normal slip. So we give it a label. There's our file name. We're going to use nearest neighbor interpolation because yes, I believe that, well, we'll look at the slip amplitude to see, but I believe that we generate more impulses than we actually need. And then finally, we just give it output file names. We've already provided all of the information describing the type of output. This point output will be output at the same points as our synthetic observations. The ground surface output is again going to be output for the Y positive node set, and similar for the domain and the fault. So we don't really need any additional information, just a unique file name here, which is what we've done. So if we look at the impulse amplitude spatial database. Okay, I see what we've done. So we are generating slip from 0 to 18 kilometers depth. So that's down beyond where we know that the fault slipped. So it's kind of overkill, but that's good because in a real scenario, you wouldn't know how deep the fault slipped. So it just gives you the amount of slip, and we're giving it negative, a negative value. So that means that, let's see, for 2D, I have to remember, let's look at our, yes, reverse, let's see, so is this, yes. 2D, this is, that's reverse slip, so that's what we want. So to run the greens functions, if you look at the, it tells you right here at the top how to run it. So this reads your PyLith app.config that you already had, plus the greens functions.config that we've just looked at. And it will automatically read that because we've switched the problem type to greens functions. So we're going to just generate our greens functions.
Charles, we have another question about the difference between nearest neighbor interpolation and linear interpolation. I think that's the question, what the question is.
Okay, the default interpolation in PyLith for any type of spatial database is nearest neighbor. That and nearest neighbor, for instance, in this case, we're looking at interpolation along a curve, which say along the fault. If you if we look at our impulse spatial database, and we use nearest neighbor for that, so it's PyLith will search for any point along that curve. It will try and find the nearest point that matches what's in the spatial database. So anything, in this case, anything above 18 kilometers is going to be assigned a value of -1. Anything below that is going to be assigned a value of 0. Now, linear interpolation, and to do that, let's see. In this case, we specifically told PyLith to use nearest neighbor interpolation. We didn't really need to do that because that's the default. The other option is if we do, oops. When we did the forward model for the fault slip, we use linear interpolation. So what that will do, if we look at this spatial database, oops. In that case, we've said, okay, from 0 to 12 kilometers depth, we want 2.5 meters of slip. And then between 12 and 15 kilometers, it will linearly interpolate down to 0. Or yeah, 2.5 meters of slip, it'll linearly interpolate to 0. So what that looks like, we can look, let's see, let's do,
I think they've got it, Charles.
Do they have it? I can, because I can show what it means is it doesn't just jump suddenly from 2.5 to 0 as it would if you did nearest neighbor. Instead, there's a linear ramp along this part right here.
I think we'll see it when you plot the inversion results.
Yeah, you're right, we will. So, okay, so I've generated my greens functions. So what, let me get rid of some of this stuff that I have here. Oops. Okay. So now we have our fault. Okay. We have, let's look at the points. So what we want to show here, let's make this bigger. So this will show our imposed fault slip at different times. And then let's do what we did again. We'll just make a displacement vector out of these points. And we'll make a vector. Points. Let's see if that works again. What happens? Let's make that bigger. Okay, so what this is going to show is these are our observation points. And we're, oh, shoot, let's forget how to, oops, that's not what I wanted to do. Oops. No. I don't want to rotate this. Nope. This drives me nuts here.
Click on the Z minus orientation.
That's the one I want, yep. Okay. So we're just going to see what happens as you apply unit slip impulses on these different different nodes. So let's see. And you can just play through the whole thing. We have 26 greens functions. Now, one thing you'll notice, they're not quite in order. That's okay. You can sort them later. But just by default, they may or may not be in order. So anyway, so for a unit slip of fault or unit slip at this given point on the fault, these are what our surface responses are at these points. So now that we have that, we have synthetic data, so we can now perform an inversion. So just oops, where did that go? There we go. Let me make this bigger. Is that big enough?
That's good.
Yep. Okay, so this is just a very simple inversion code that we wrote that will take the simulated earthquake data that we produce. So that's the displacements at that set of points. It will also read in the Green's functions that we just generated, and then it'll form a very simple inversion using that what I showed you earlier in the presentation. And so you're going to need NumPy and H5Py for this particular part, which you should have as part of PyLith. So we have we just define a function that we use more than once. So what this does, this reads our impulses, and this is the file that it takes arguments. Let's see down here. You can give it an impulse file, the response file, and then your data file, a file that defines your penalty functions, and then finally your output file. So let's see. I can show you very quickly what the penalty file just, all I did was just factor of 10 increase, going from, this is essentially how much you're smoothing your result, from hardly any to very strongly smoothed. So anyway, so we give it an impulse file, response file, data file, penalty, output. And this is where we read the impulses. Read in the file, and then the HDF file is organized in a way so that this will give us our coordinates in this array right there. So that's our impulse coordinates. We're going to get the slip that we imposed at those coordinates, and that's going to be 26 different values of slip. So that's our impulse values. And then our indices is where the impulse value is not equal to 0. So then we just select the impulse indices that were actually used, or our impulse coordinates that were used, and our impulse values that we used. Okay. Then we sort these. These are just convenience, or actually very handy sorts of functions that you'll find in NumPy, which this will give you the indices that would sort an array. And here we're sorting it by the y coordinate. And so then we have sorted arrays, your sorted coordinates, your sorted values. Then we just close that file. Let's see, I guess we read, we get impulses and responses in this function. So again, we do the same thing for the responses. We get the response coordinates from our HDF5 file. We get the response displacements, so that's X and Y displacements. And then we sort these responses by the same indices that we used up here for our impulses, so that we have ordered sets that match each other. And then we just close it, and we return all those sorted arrays. This is another function that just gets our data. So we read in the HDF5 synthetic data file. We get the coordinates of those data points. We get the simulated displacements at those data points. Then we close the file, and this just returns those values. This is the part where we've already seen. These are just our command line arguments. Just some error messages if you don't give it some information that it needs. And then here's where we actually use that one function that we looked at to get impulses and responses. Here we get our data. Then we just load in our penalty file, which we just looked at down here. I don't know if you can see it or not, but there it is. And then we set up, I'm calling it an A matrix. It's actually what I call the G matrix in that slide. So we have our number of parameters, which is just our number of impulses. Our number of observations is twice the number of data points because we have X and Y displacements. And then we take these response values that we got up here, and then that's just our G matrix. Then we create a diagonal matrix that we're going to use that to multiply our penalty parameter times this identity matrix. Then we get our data vector. So we have our data values, we flatten them out so it's just a single array of X and Y displacements. And then our a priori values are just zeros here. So that's what this part is right here. So just zeros. The number of inversions we're going to perform is just the size of our penalty parameters file. And then we'll have an empty array to put our inversion results into. And then we have, yes, there's our X coordinates, or our coordinates for the inversion results. Then we're going to loop over a number of inversions. For each one, we'll have a penalty parameter that we apply. Our penalty matrix is just this penalty parameter for the given inversion times that identity matrix. And so our total design matrix is we just stack the G matrix that we defined up here with this penalty matrix. And then we'll take the transpose of that. And then we form the generalized inverse, which is again from the slides that I showed. And our solution is then just the generalized inverse multiplied by the data vector that we defined up here, which is just the regular data plus our a priori values, which we're assuming to be 0. And then our predicted values is our original G matrix times our solution. And then we can compute the residual, where we take the data values minus our predicted solution. And then we can also compute a residual norm. And then we just output the results. This is just saves things as columns of data that will save to this output file. So the way that we run this, we look here. This is, we'll run it from the reverse directory because that's where all of our data and our Green's functions are. So we're running something that's 2 levels up. Let's see, will it do like this? I don't know if it will. Let's see if it will. Yep. Okay, so there it ran our inversion. And for each case, it gives us a summary, the imposed penalty parameter, what your residual norm is. So that doesn't tell us a lot, but it tells us that the more you smooth it, the worse your fit. But of course, also totally unsmooth is probably not reasonable either because you get a very rough solution in that case. So we run our inversion, but doesn't tell us a lot. So what we want to do is look at our inversion results. Okay, so to do that, we'll just plot up our results, which are in this output file here. We've given it that file name as part of the parameters for this inversion code. So now we have another Python code. We'll look at that. And we'll make that bigger. Okay. Okay, now this one requires matplotlib in addition to the others that you already had. So you may or may not have that unless you've installed it yourself. But it's meant to work essentially like MATLAB, the plotting is. So then for this one, all we do, we define some colors that we're going to use for plotting. This is just a regular Python list of colors. We're going to plot the solution color or in black, the true solution, and these are our estimated solutions using different values of the penalty parameter. So we have another, here I'm going to have a sip of water here. We have another function that essentially just gets our the true solution along with the coordinates of the fault. So we open up the HDF5 file. So this was from our eqsim.config simulation. We get our solution coordinates. We get our imposed slip. And then again, we sort it by y coordinate. So that's what we're doing here. So sort both the coordinates and the imposed slip by y coordinate. And then we're going to reverse the sign since we're actually looking for the negative of this. Okay, then the main part of the code, this is where we provide our command line parameters. So we have a, let's see, solution file. We have, and then we have our output file with the predicted values. So down here, that's, and then, all right, this is the predicted file that we created with our inversion code. So those are the only two inputs we need, the true solution and our predicted solution. So we get the solution file with the function we just saw. We get the predicted solution with just loading in this file that we just created with the inversion code. And here we have our predicted coordinates and our predicted slip. And then all we do is we first plot the true solution. That's going to be with the black line. Give it some labels on the plot and then some limits on the y-axis. And then we're going to loop over our inversion results, and for each case we'll superimpose a new line with the predicted solution for a given penalty parameter. Oh, also down here at the bottom, if instead of writing it to the display, you could also just save it as a PDF file if you want. So if you wanted to do that, instead, you could uncomment this, this command right here. So we'll just run that. Right here, I've already shown how to do it. Okay, so these are our predicted results. If we go back and look, I didn't plot a legend on here. Can you see that if I move it over there? Hopefully. If we look at the colors, so the cyan solution is the one with the, let's see, the smallest amount of smoothing. So that's our true solution is shown here in the black. So this is what we impose to generate our synthetic data. This cyan colored line is our solution when we have the smallest amount of smoothing. And what you can see, it overshoots on the edges, but it actually does a pretty good job of matching. And then as you go to the different colors, we have red, blue, green. So red is a little smoother, blue is a little smoother, green is smoother. Then we have orange, which is getting quite smooth. And then we get very smooth, which and also very constrained to be close to zero, is down here. Actually, I shouldn't say smoothing. The higher the penalty parameter, the more it is constrained to lie close to zero. So that's what we're doing here with the purple. And then finally, the yellow solution is almost completely constrained to be zero. Actually, I believe as exercises for the readers, rather than the simple penalty that we imposed, which is just essentially a minimum length solution, the next level would be a true smoothing one where you approximate the gradient in the solution, and you might minimize the gradient using a different a priori solution. So anyway, that is the, we've gone through the reverse slip 2D example. Are there any questions related to that?
No signs of typing yet.
Okay, either they completely understand it or they're completely baffled. So, okay. Well, if we think of some later on, we can email or ask later. So I'm going to close some of these files.